20 miles above your head, in a layer of the atmosphere almost nobody thinks about, something can happen right now that determines whether your entire region freezes solid 3 to 6 weeks from today. It's not a cold front. It's not a storm system you can see coming on a 5-day forecast. It's an event that unfolds in the stratosphere, so far above the clouds that it has nothing to do with the weather you're actually feeling outside your window. And yet it is, without exaggeration, one of the single most reliable predictors meteorologists have for when temperatures across the United States are about to fall off a cliff. It has a name most people have never heard, and it just did something earlier this year that led directly to one of the most damaging cold outbreaks North America has seen in years. Today, we're breaking down exactly what a sudden stratospheric warming event actually is, how it triggers the kind of temperature crash that can kill people and shut down entire regions, and what current signals suggest about the pattern setting up for the months ahead. Here's why this particular mechanism deserves your attention over the dozens of other weather stories competing for it right now. Ordinary storm forecasting works on a scale of days. Meteorologists can see a system coming, model its path, and issue warnings roughly a week out at the very most before confidence starts to break down. What we're about to walk through operates on an entirely different timescale, one that lets forecasters flag a coming disaster over a month before it actually arrives at ground level, using a signal that comes from literally the opposite direction most people would expect to look. Not a satellite image of clouds, a measurement of wind speed 20 miles straight up in a part of the sky that has no clouds in it at all. Let's start with the event that just proved, in the most brutal way possible, exactly how powerful this mechanism actually is. In mid-January 2026, meteorologists tracking the stratosphere detected the unmistakable signature of a sudden stratospheric warming event, a genuinely bizarre atmospheric phenomenon where temperatures roughly 20 miles above the Earth's surface spike dramatically, sometimes by several tens of degrees in the span of just a few days. That might sound like a purely academic curiosity happening so far above the ground that it couldn't possibly matter to anyone standing outside in Ohio or Texas. It matters enormously, because that sudden warming doesn't stay contained in the stratosphere. It disrupts the polar vortex, the enormous persistent pool of frigid air that normally sits locked, in place over the Arctic throughout winter, held together by a tight, fast-flowing ring of high-altitude winds. When a sudden stratospheric warming event strikes with enough intensity, it can weaken, stretch, or in the most extreme cases, physically split that vortex apart. And when the vortex loses its grip, the Arctic air it was containing doesn't just sit there. It spills outward and southward, riding the jet stream down into the middle latitudes, directly into the path of tens of millions of Americans. That's precisely what happened over the following weeks. The disruption that began in the stratosphere in mid-January propagated downward and outward, and by the final week of the month, the effects reached the surface in dramatic fashion. On January 26, 2026, a severe winter storm swept across the country, and the imagery meteorologists were tracking that day tells the whole story on its own. Weather models showed the freezing line, the boundary separating above freezing and below freezing air, reaching deep into Texas, while forecasters simultaneously tracked the stratospheric polar vortex sitting directly overhead at roughly 20 miles up, in near-perfect vertical alignment with the jet stream racing along about 3.5 miles above the surface. When those two features line up that precisely, meteorologists know they're looking at exactly the setup capable of producing an exceptionally severe, exceptionally cold storm, and that's exactly what unfolded. The storm and the broader cold wave that followed devastated an extraordinary swath of the continent. Hundreds of thousands of people lost power across the south as ice accumulated on tree branches and power lines and brought them down. More than a foot of snow fell across parts of the Midwest and Northeast. Bitter cold settled in and lingered for days, with the reach of the frigid air extending remarkably far south, all the way through Mexico, Central America, and as far as Belize, an almost unbelievable extent for what began as a disturbance in the stratosphere above the Arctic Circle. By the time the broader cold wave finally dissipated in mid-February, it had been directly linked to at least 22 deaths and roughly $4 billion in damage across Canada, the United States, Mexico, the Greater Antilles, the Bahamas, and Central America. A staggering toll for an event that most people experience simply as a really bad cold snap, without ever understanding the atmospheric chain reaction that produced it. Here's what makes this particular kind of temperature crash so genuinely dangerous compared to an ordinary winter storm. And it comes down to a factor climate scientists have increasingly flagged as making these events worse, not better, in a warming world. The storm's severity was intensified specifically because it followed what had been an unusually mild start to winter across much of the country. Researchers studying the event noted that Earth's overall warming trend, driven by greenhouse gas emissions trapping heat in the atmosphere, had contributed to a warmer than average ocean surface heading into the disruption. And that warmth, combined with the sudden southward plunge of Arctic air, created an especially sharp temperature contrast exactly where storms need that contrast to intensify rapidly. In other words, a warming climate doesn't necessarily mean winter cold snaps disappear. In some cases, it can make the whiplash between unusually mild stretches and sudden, severe cold outbreaks even more extreme and more dangerous, precisely because the atmosphere has more energy and more contrast to work with when a disruption like this one occurs. It's worth understanding precisely how meteorologists actually define and detect a sudden stratospheric warming event, because it isn't a vague, subjective label applied after the fact. The standard scientific definition centers on measuring winds at a specific altitude, roughly 10 hectopascals of atmospheric pressure, which corresponds to around 18 to 19 miles above the surface, right in the heart of the stratosphere where the polar vortex normally circulates. Under typical winter conditions, those winds blow steadily from west to east, the signature of a healthy, tightly organized vortex holding cold air in place over the pole. A sudden stratospheric warming event is formally defined as occurring when those winds actually reverse direction, flowing from east to west instead, combined with a rapid temperature spike in the polar stratosphere of potentially several tens of degrees within a matter of days. That wind reversal is the unmistakable fingerprint scientists look for, and it's tracked continuously by dedicated monitoring networks and satellite data, specifically because catching that reversal early is what gives forecasters their crucial multi-week head start. To understand why a sudden stratospheric warming event has this kind of outsized power over surface weather, it helps to actually understand the layered structure of the atmosphere itself. The weather you experience day to day, the storms, the rain, the wind, all of it happens within the troposphere. The lowest layer of the atmosphere extending up to roughly 7 miles above the surface. Above that sits the stratosphere, stretching from about 7 miles up to roughly 30 miles, a layer that's normally remarkably stable and disconnected from surface weather. But the stratosphere and troposphere aren't actually sealed off from each other. They interact through atmospheric waves, similar in principle to the waves you can see in the jet stream dipping south and swinging back north, except these particular waves propagate vertically, moving energy and disruption upward from the surface into the stratosphere, and crucially, sometimes moving the effects of a stratospheric disruption back downward into the jet stream weeks later. When a sudden stratospheric warming event weakens or splits the polar vortex, that disruption can take anywhere from a few days to several weeks to fully propagate down and reshape the jet stream at the surface, which is exactly why meteorologists treat a confirmed stratospheric warming event as a genuine early warning signal, a chance to say, with real confidence, that severe cold is likely coming to specific parts of the country roughly 3 to 6 weeks out, even before any conventional weather model would normally be able to see that far ahead with any real skill. This isn't a new or untested forecasting technique, and the January 2026 event fits into a well-documented pattern researchers have tracked across multiple recent winters. A remarkably similar sequence played out in February 2021, when a sudden stratospheric warming event in early January was followed roughly a month later by the catastrophic Texas freeze, an event so severe it knocked out the state's power grid for days, caused temperatures to fall 25 to 50 degrees Fahrenheit below average as far south as the Gulf Coast, and brought snow and ice accumulation to Houston, contributing to one of the deadliest winter weather disasters in modern Texas history. Just 2 years before that, in January 2019, a weakened jet, stream tied to polar vortex disruption, sent bitterly cold air plunging into the Midwestern United States and eastern Canada, killing at least 22 people, with wind chills in parts of Minnesota dropping toward negative 50 degrees Fahrenheit. And just 1 year before the 2026 event, in January 2025, another southward migration of the polar vortex following an Arctic front produced the coldest January much of the continent had experienced in at least a decade, pushing snow and ice into regions of the deep south that almost never see it. Notice the pattern across every one of these events. A disruption begins high in the stratosphere, often barely making headlines outside of specialist meteorological circles when it's first detected. Weeks later, the consequences arrive at the surface as a severe, sometimes lethal cold outbreak, catching a large portion of the public off guard specifically because the connection between something happened in the stratosphere 3 weeks ago and it's now dangerously cold in Texas isn't something most people are watching for. That's precisely the gap this kind of reporting exists to close. The economic ripple effects of these events extend well beyond the immediate storm damage and casualty figures, and they're part of why energy markets, agricultural operations, and utility companies watch stratospheric warming signals every bit as closely as meteorologists do. Natural gas prices, for instance, tend to spike sharply in the days surrounding a confirmed polar vortex disruption, as utilities across the affected regions scramble to meet suddenly surging heating demand precisely when supply chains are simultaneously being disrupted by the same cold and ice damaging infrastructure. The 2021 Texas freeze offered the starkest possible lesson in need. This dynamic, when the state's largely isolated power grid, unprepared for the intensity and duration of the cold, saw generating capacity fail across multiple fuel sources simultaneously, leaving millions without power for days in freezing conditions, and ultimately contributing to a death toll that took months to fully tabulate. Grid operators across the country have since incorporated stratospheric warming monitoring more directly into their own seasonal risk planning, treating a confirmed disruption event as a genuine trigger for reviewing winterization procedures and emergency generation capacity, well before the resulting cold air actually arrives at the surface. It's also worth understanding that not every sudden stratospheric warming event produces an identical outcome, because the specific way the polar vortex responds matters enormously for which parts of the country actually end up in the cold air's path. Sometimes the vortex simply weakens and stretches out of its normal circular shape without fully breaking apart, a scenario that tends to nudge cold air towards specific regions, depending on exactly how and where the stretching occurs. In more extreme cases, the vortex can physically split into two or more separate lobes, each one then wandering independently and potentially delivering cold air to completely different parts of the hemisphere, depending on where each lobe eventually settles. Forecasters spend the weeks following a confirmed stratospheric warming event closely tracking exactly which of these scenarios is unfolding, because the difference between a stretched vortex and a fully split vortex can mean the difference between a cold outbreak concentrated in the northern plains versus one that reaches all the way into Texas and the Gulf Coast, exactly the kind of detail that turns a vague seasonal outlook into an actionable forecast for specific states. Forecasters spend the weeks following a confirmed stratospheric warming event closely tracking exactly which of these scenarios is unfolding, because the difference between a stretched vortex and a fully split vortex can mean the difference between a cold outbreak concentrated in the northern plains versus one that reaches all the way into Texas and the Gulf Coast. Exactly the kind of detail that turns a vague seasonal outlook into an actionable forecast for specific states. Ensemble forecasting, running dozens of slightly varied simulations of the same evolving atmospheric pattern rather than relying on a single deterministic model, has become the primary tool meteorologists use to narrow down these possibilities in the weeks following a confirmed disruption. If the overwhelming majority of ensemble members agree that cold air is heading toward a specific region, forecasters can issue that outlook with real confidence, even weeks before a conventional short-range model would normally have any skill at all. If the ensemble members disagree significantly about exactly where the cold will settle, that uncertainty itself becomes useful information, signaling to emergency planners and utilities that they may need to prepare contingencies for multiple possible outcomes rather than a single fixed forecast. So what does all of this mean for where we sit right now, heading into the back half of 2026? This is genuinely the question meteorologists start asking every single year around this point in the calendar, well before the first cold front of the season has even arrived. Because the setup for a severe winter doesn't begin in December. It begins with the broader atmospheric and oceanic patterns already taking shape months earlier. Long-range forecasters have been tracking a moderate El Niño pattern developing through the second half of 2026 with sea surface temperatures in the benchmark Niño 3.4 region of the tropical Pacific running roughly 1.3 degrees Celsius above normal as of recent measurements, a signal strong enough that NOAA's Climate Prediction Center has already factored it heavily into monthly outlooks. El Niño winters tend to favor a specific, though far from guaranteed, set of patterns across North America, typically leaning toward a wetter, more active storm track across the southern tier of the country and the potential for a more variable, swing-prone pattern across the northern and central states, exactly the kind of setup that has historically produced sharp temperature whiplash rather than one long, steady, predictable cold season. Seasonal outlook services that specialize in longer-range pattern forecasting have already begun sketching out what this winter might look like, and the early signals point toward genuine volatility rather than a single dominant theme. One recent long-range winter outlook described the upcoming season as likely to feature fast-moving weather systems, sudden cold snaps, and brief but intense snowy periods across the middle of the country, punctuated by milder breaks that could interrupt the wintry stretches before the next disruption arrives. The Great Lakes and Plains were specifically flagged as likely to see sudden snow squalls and bursts of bitter cold, while the Northeast was described as facing one of the more genuinely complicated winter patterns of recent years, with small shifts in storm tracks potentially determining whether a given system arrives as rain, sleet, freezing rain, or accumulating snow Precisely the kind of forecast uncertainty that makes it critical for residents to keep watching updates as the season actually approaches, rather than relying on a single outlook issued months in advance. Regional forecasters have gone even further in sketching out specific expectations. Coastal communities in the Northeast are being told to expect more rain and mixed precipitation events than a typical snowy winter, while inland areas across the same region face the opposite risk, several rounds of heavy, wet snow, concentrated particularly during January and February, almost mirroring the exact time frame when the 2026 disruptions struck. Meanwhile, current summer into fall monitoring has flagged the Midwest as trending toward a cooler shift as autumn progresses, even as the Central Plains contend with persistent dryness and strengthening drought conditions heading into the colder months, a combination that can actually make a subsequent cold outbreak feel even more severe, since dry ground loses heat more efficiently than moist soil, amplifying how quickly and how deeply surface temperatures can fall once genuinely cold air finally arrives. This isn't a phenomenon unique to North America either, and looking at how the same mechanism has played out elsewhere in the world reinforces just how consistent this relationship between stratospheric disruption and surface cold actually is. In early 2018, a sudden stratospheric warming event triggered what British meteorologists nicknamed the Beast from the East, an outbreak of Siberian air that plunged temperatures across the United Kingdom and much of continental Europe to levels not seen in years, closing schools, disrupting transportation networks, and contributing to dozens of deaths across the continent. The same broad mechanism, a stratospheric disruption weakening the vortex and allowing cold air to spill into the mid-latitudes, has now been documented, driving severe cold outbreaks on both sides of the Atlantic repeatedly over the past decade, giving meteorologists an increasingly robust body of case studies to refine exactly how quickly and how severely a given disruption is likely to translate into surface-level danger. None of this constitutes a guarantee that a sudden stratospheric warming event is imminent this coming winter, and it's important to be genuinely honest about that limitation. Stratospheric warming events don't occur on a fixed, predictable schedule. Some winters see none at all. Others, like the winter of 2025 into 2026, saw the atmosphere deliver not one, but effectively two separate significant disruptions within the span of a few weeks, first in mid-January and then again in early February, each one contributing to the broader cold wave that battered the continent through much of that stretch. What meteorologists can do and what makes this specific area of forecasting genuinely valuable rather than just alarmist is watch the stratosphere continuously throughout the winter months, monitoring wind speeds around the polar vortex's core and comparing them against long-term averages, because a rapid weakening of those core winds is precisely the early signature that precedes a full disruption event. When that signature appears, it gives forecasters a genuine 3 to 6 week head start on telling the public that a serious, potentially dangerous temperature crash is likely on the way. Time that matters enormously for utilities preparing their grids, for local governments planning emergency shelter capacity, and for individual families deciding whether to winterize their homes and vehicles before the cold actually arrives rather than scrambling once it's already here. That multi-week head start translates into genuinely concrete preparation steps for anyone living in a region likely to be affected. Households in areas prone to these outbreaks are typically advised to insulate exposed pipes and know how to shut off water at the main valve before a hard freeze arrives, since burst pipes remain one of the most common and costly forms of damage during a severe cold outbreak. Vehicle batteries lose a significant portion of their effective capacity in extreme cold, making a routine battery check well worth doing before the coldest air of the season actually settles in. And emergency management officials in regions with a documented history of stratospheric warming-driven cold snaps generally recommend having several days of food, water, and any necessary medication on hand, precisely because these events have repeatedly demonstrated the capacity to knock out power and disrupt supply chains for days at a time. None of this requires panic. It requires exactly the kind of lead time a confirmed stratospheric warming event provides, time that's only useful if people actually understand what the signal means and start preparing before the cold, rather than after it. That's the real mechanism behind this year's most consequential weather story. Not a single storm system you can watch approach on a radar map, but an invisible disruption unfolding 20 miles above the Arctic, capable of reshaping temperature patterns across an entire continent weeks before anyone at ground level feels the first gust of genuinely bitter air. The January 2026 event already proved exactly how severe the consequences can be. 22 lives lost, billions of dollars in damage, and cold air reaching as far south as Central America from a disruption that began in a layer of the atmosphere most people have never even heard of. Meteorologists are watching the stratosphere closely again as this year's pattern continues developing, because history makes one thing genuinely clear. When the polar vortex breaks down, the consequences eventually come looking for all of us. Stay with this channel, because we'll be tracking every stratospheric warning sign as it develops. And this is exactly the kind of story where staying a few weeks ahead of the pattern could make a genuine difference for how you and your family prepare.